All right, settle down, please. So we got initiated into coordinate geometry uh, early in class 11 and got introduced to the basic foundation of coordinate geometry in the form of straight lines. Now we extend that learning a little more and get into uh, the rudiments of circles, basic rudiments of circles. Now, needless to say, if there is a circle, then it's completely and uniquely defined by two things: location of its center and its radius. Center and radius, right? So, x1, y1, the center of a circle with radius r, is given by x minus x1 whole squared plus y minus y1 whole squared equal to r squared, which means, what it means is, if xy be any point on the circle, then its distance from x1, y1 will be equal to the radius. That's what this statement means. Square root of this is the distance of any point xy on the circle from the point x1, y1 equal to the radius r of the circle, right? So any point x1, xy on the circle will satisfy this equation. So this could be looked upon as the equation of a circle. It could be looked upon as the equation of a circle, right? Now, you could simplify this as x square plus y square minus 2x1x minus 2y1y plus x1 squared plus y1 squared minus r squared equal to 0. Right? Where x1, y1 is the center. Customarily, this minus x1 is written as g, minus y1 is written as f. It is customary to write minus x1 as g and minus y1 as f. In which case, this becomes x square plus y square plus 2gx plus 2fy, and this x1 squared plus y1 squared minus r squared is customarily written as some c. So in which case, realize that if this is the equation of a circle, x squared plus y squared plus 2gx plus 2fy plus c equal to 0, then evidently the center of the circle is given by x1 comma y1, which is minus g comma minus f, is the center of the circle, because minus g would be x1, minus f would be y1. So if somebody gives you the equation of a circle in this form, you can readily say that minus half the coefficient of x and minus half the coefficient of y will give you the center of the circle. You late? Sit down, I'll talk to you later. And in which case, the radius r of the circle, realize this x1 squared is g squared, y1 squared is f squared. So then the radius r of the circle is given by root g square plus f square minus c, is given by root g square plus f square minus c. That's the radius of the circle. So given the circle in its conventional form, x square plus y square plus 2gx plus 2fy plus c equal to 0, minus half the coefficient of x and minus half the coefficient of y will give you the center of the circle, and root g square plus f square minus c will give you the radius of the circle. A special case of a circle would be when g square plus f square minus c is 0. It's going to give you a circle with 0 radius. And that circle is called the point circle. A point circle will coincide with its center completely. Just a point is a point circle with 0 radius. Right. Now, Again, you could look upon, I mean, after all, if this is a circle, you could also have a circle whose center is 0, 0. Origin could be the center of a circle. Or rather, the center could be selected as the origin. The center could be, says, the circle is given and you can select the center as the origin, right? Because the choice of the coordinate axis is entirely yours, right? And if r is the radius of the circle and if x, y be any point on the circle, then its distance from 0, 0 will be equal to r. So the equation of the circle whose center is the origin is equal to r square, right? So this is the general equation of a circle. This is the equation of a circle whose center is the origin. Clear? Now, while I build all this business of coordinate geometry with you, I will go in a very phased out manner, but there are certain things that I'm going to go very slow with. I will let you take your own time to assimilate everything while I communicate all of this to you. But then there is some symbolism associated with it, and the symbolism, if understood in circles, will get extended into parabola, will get extended into ellipse, and then eventually hyperbola. So it's a one-time learning. You learn it in circles. By the time I come to a parabola, you'll realize I have already done it. And then by the time I'm in ellipse, you'll see it's a repetition. And then when it's hyperbola, you'll get bored. All right. Now, just this expression is called S. Just the expression. This is only an expression. This equal to 0 is an equation. This expression is referred to as S, which is like a x square plus y square plus 2gx plus 2fy plus c is an expression. This expression would be referred to as S. S equal to 0 will be a circle. S equal to 0 will be a circle. But otherwise, this expression would be referred to as S, right? Or even this equation, which could be written as x squared plus y squared minus r squared equal to 0, this will also be referred to as S. So this S would be the general expression, and this S would be the expression which is capable of representing a circle whose center is the origin. So S could be this, or it could be this. So either this S equal to 0 or this S equal to 0 will represent a circle. This S equal to 0 will represent a circle whose center is minus g minus f, whose radius is root g square plus f square minus c. This S equal to 0 will represent a circle with center 0, 0 and radius r. But until and unless you equate it to 0, its status is no more than an expression. It will just be looked upon as another expression, any other algebraic expression, right, of second degree. Second degree because the highest power of x or y or a combination here is 2. So this is a second degree expression, right? Now, look, if there are two circles and the distance between their centers is d. Distance between their centers is d. R1 is the radius of one circle and R2 is the radius of the other circle, right? In this case, realize that the circles don't intersect and the circles do not intersect very clearly. In this case, how does one check if the circles don't intersect? If the distance between their centers is greater than the sum of the radii. So this case is commensurate with d greater than R1 plus R2. So if the distance between their centers is greater than the sum of the radii, you can claim that the circles don't intersect at real points. They do intersect, but they intersect at two imaginary points, right? So they don't intersect at real points. And Now push this circle towards the circle. This circle is of radius r1, this circle is of radius r2. The distance between their centers is g. In this case, g is equal to r1 plus r2. Distance between their centers is sum of the radii, and the two circles intersect at two coincident points. The two circles, these are two circles, they intersect at two coincident points. This is the coincident point. These are the two coincident points. The two circles will always intersect at 2 points. Those 2 points can be imaginary, or in this case, they could be coincident. Right? Or in this case, two coincident points. So mathematically speaking, clear? And then you push one circle into the other one a little more. C1, C2. And if you push it further in, then the next step would be this. And if you again push the two circles, one circle into another, then this, right? These are the various conceptual orientations of the circle. Now, in this case, the distance between their centers is difference of the radii. In this case, realize that R1 minus R2 is the distance between their centers, yes or no? Do you realize that? The distance between their centers is what? R1, the radius of the bigger circle, minus R2, the radius of the smaller circle. So this is the case where the distance is R1 minus R2, right? Now, if you hammer this circle a little away, like this, then you will get this orientation. That means the distance becomes greater than R1 minus R2 in this case. Distance becomes greater than R1 minus R2. So, in general, to make sure that it's not negative, magnitude of R1 minus R2, because you do not know which one is bigger, right? So, in this case, distance is greater than R1 minus R2, but less than R1 plus R2, less than R1 plus R2. Yes or no? Are you there with me? Right? So, two circles intersect at two distinct real points. In this case, they are two distinct real points. The two circles intersect at two distinct real points, namely A and B. And when would that happen? When the distance between their centers is less than the sum of the radii, but greater than the magnitude of the difference of the radii. Right? This, we say the two circles are touching each other internally. We say that they are touching each other internally. They have a common tangent like this. In this case, the two circles touch each other externally. See, again, you have to realize the difference between touching and cutting. These are two different terminologies used in coordinate geometry. This is touching, whereas this is cutting. There is difference between touching and cutting. Touching is a case which leads to a common tangent. Cutting leads to a second. Cutting will lead to a second, whereas touching will lead to a tangent. When this point comes closer and closer and closer and closer and closer to this point, we have two coincident points, and that will lead to touching. If you have two distinct points of intersection of two different entities, and you bring one point closer and closer and closer to the other point, it leads to touching. So touching is a case of common tangency. Cutting is a second. Cutting will lead to a common chord or a second. Do you understand the difference between touching and cutting then? Okay. So this is touching externally. This is touching externally. This is touching internally. This is touching internally. This is touching internally. This is one circle completely inside the other circle. Now, if you push this inner circle further in, the distance will become less than R1 minus R2. So, in this case, the distance is less than mod R1 minus R2. The two circles once again don't intersect. The two circles once again are intersect at imaginary points. No issues, right? Another form of the equation of a circle which is widely used. Look, if this is a circle and this is the center C of the circle. First of all, let me ask you something very fundamental first. Very fundamental. Given the center of a circle and given the radius of a circle, how many circles will exist? Given the center of a circle and given the radius of a circle, given the center of a circle, given the radius of a circle, how many circles will exist? Why? Sphere. Realize that. Because given the center, given the radius, the circle could be like this. Given the center, given the radius, the circle could be like this. Given the center, given the radius, the circle could be like this. Isn't it? So out of all these circles that you can generate with a given center and a given radius, you will generate a sphere. Isn't it? But then, if they tell you that the center of the circle is so on this and this, the radius of the circle is this, and the circle lies in the xy plane, then the circle is unique. If they tell you, if they describe to you the plane of the circle, then they give you the center of the circle and the radius of the circle, then the circle is unique. That's to be understood, right? So then we're talking of a circle in the xy plane, given the center and given the radius of the circle. Now, let's say they give you a circle whose diameter is constituted by AB. That means the endpoints of the diameter are x1, y1 and x2, y2 are the endpoints of the diameter of a circle. Clear? So A and B are known, the endpoints of the diameter of a circle. And now, if P x comma y be any point on the circle, if P x comma y be any point on the circle, equation of the circle means connecting x and y. Equation of the circle would mean connecting x and y. Obviously, if P is any other point on the circumference of the circle, then what would this angle be? Angle in a semicircle, so 90 degrees. That means the slope of PA into the slope of PB will be -1, right? Slope of PA into slope of PB. And what's the slope of PA? Y minus y1 by x minus x1. What's the slope of PB? Y minus y2 into by x minus x2. Right? Multiply and coagulate terms. X minus x1 into x minus x2 plus y minus y1 into y minus y2 will be the relationship between the x and the y coordinates of any point on a circle if the endpoints of a certain diameter are x1, y1 and x2, y2. So this then is the equation of a circle, form of the equation of circle given in terms of the endpoints of the diameter of the circle, given in terms of the endpoints of the diameter of the circle. So this equation given in terms of the endpoints of the diameter of a circle. Now, like I said, I'm going to designate this expression as S. X squared plus y squared plus 2gx plus 2fy plus c, or S would be x squared plus y squared minus a squared. In either case, if you put S equal to 0, you will get the equation of a circle, right? This would be a circle with center 0, 0 and radius a. This would be a circle with center minus g minus f and radius root g square plus f square minus c, right? Now, when I say S1, this is what I would mean. If I say S1, then I would mean to replace x and y by some point x1, y1. This xy is general, but when I replace x by x1 and y by y1 in this expression, I would then call that expression S1. S1. So S1 would be a number obtained by replacing x by x1 and y by y1, where x1, y1 is just any point, anywhere. Any point, anywhere, not necessarily on the circle. It could be anywhere. Then S1 would mean x1 squared plus y1 squared plus 2gx1 plus 2fy1 plus c, or if the circle has, if it's this S, then S1 would mean x1 squared plus y1 squared minus a squared. Right? You know what I'm saying? This is the meaning of S1. I'm introducing terminology to you right now. Now, if this is a circle, let's say this is a circle S equal to 0. This is a circle, let's say S equal to 0. Let's say in a more general sense, let's say S is x squared plus y squared plus 2gx plus 2fy plus c equal to 0 is the circle, right? What's the center of the circle? Right. Now, if there is a point P x1, y1, in the xy plane, it can have three possible locations. It could be inside the circle, it could be on the circle, or it could be outside the circle. Very clearly, if the point P is inside the circle, then the distance of P from the center must be less than the radius, right? So what's the radius of the circle? Radius of the circle is root g square plus f square minus c is the radius of the circle, right? So if the point P is inside the circle, then very clearly Cp must be less than the radius. So Cp squared must be less than radius squared, and Cp squared is x1 plus g whole squared plus y1 plus f whole squared less than r square, which is g square plus f square minus c. If the point P is inside the circle, then the distance from P must be less than the radius, which leads to this, which then gives me x1 squared plus y1 squared plus 2gx1 plus 2fy1 plus c less than 0. Hey, but what is this? This is S1. Replacing x and y by x1, y1. So S1, if S1 is less than 0, then x1, y1 lies inside the circle. If S1 is less than 0, then the point P will lie inside the circle, right? Similarly, if x1, y1 was outside the circle, then this would have been greater than the radius, this would have been greater than 0, S1 would have been greater than 0. Yes or no? You know what I'm saying? So, if x1, y1 was outside the circle, then S1 would be greater than 0. And obviously, if x1, y1 was on the circle, then this would be equal to g square plus f square minus c. So S1 then would be equal to 0. Clear? So that's how you figure out the relative orientation of a point with respect to a circle, inside, on, or outside the circle, as is relevant. And whether it's this general circle or it's this circle, x squared plus y squared minus a squared, this equal to 0. Even for the same circle, whatever I say for this circle will be true for this circle. Whatever I say for this circle will be true for that circle in terms of S. So if I write S, that expression would be true for a circle, general circle with center minus G minus F, will also be true for a circle with center 0 0. It does not matter. Clear? So even in this circle, S1 less than 0 will give me x1 y1 inside the circle, S1 greater than 0 outside, S1 equal to 0 on the circle. Fair. Now, another important thing, let's say if this is a circle, say a circle x square plus y square plus 2gx plus 2fy plus c equal to 0, where S is only this expression and this equal to 0 is the circle, right? So let's say this is a circle and its center obviously is minus G minus F, minus G minus F, right? And if there is a point P on the circle, if there is a point P on the circle, then at that point a tangent could be drawn to the circle. This is a tangent at x1 y1. This is a tangent at x1 y1, yes or no? And when would this be a tangent at x1 y1? If the radius at this point is perpendicular, right? Now, obviously, given a point x1 y1 on the circle, you want to find the equation of the tangent at that point. You want to find the equation of the tangent at that point to the circle. Now, what's the slope of CF? CP. Slope of CP is very clearly y1 plus f divided by x1 plus g, right? This minus this divided by this minus this. That's the equation of CP. And what's the slope of the tangent? Slope of the tangent would be minus 1 by this, minus 1 by this. Slope of the tangent will therefore be minus x1 plus g divided by y1 plus f. That's the slope of the tangent. That's the slope of the tangent. Now, given a point, and given the slope, I can find the equation of the line, right? So the equation of the line, equation of the tangent at x1 y1 is y minus y1 by x minus x1 equals the slope, which is minus x1 plus g divided by y1 plus f. x1 plus g divided by y1 plus f. This would lead to the equation of the tangent at x1 y1. Yes or no? Right? Now, one of the things is for sure that x1 y1 lies on the circle, so will satisfy the equation of the circle, right? So since x1 y1 lies on the circle, s1 will be 0. S1 would be 0. That means x1 squared plus y1 squared plus 2gx1 plus 2f(y1) plus c must be 0. Yes or no? Which means x1 squared plus y1 squared, x1 squared plus y1 squared could be written as minus 2gx1 minus 2f(y1) minus c wherever required, right? Now, without wasting time on simplification, if you cross multiply, then on one side you will find a x1 squared plus y1 squared coming. And that x1 y1 squared you replace by this. You replace by minus 2gx1 minus 2f(y1) minus c. And when you accomplish that, then the final equation of the tangent that's going to emerge out of it is going to be the following. I mean, using this and x1 squared plus y1 squared. This would be the equation of the tangent at x1 y1 to the circle s equal to 0. This would be the equation of the tangent x1 plus y1 plus g into x plus x1 plus f into y plus y1 plus c equal to 0. Plus c equal to 0. That's the equation of the tangent at x1, y1 to the general circle. Now, for the more specific circle with center as the origin, that is, if I have the circle S, which is x squared plus y squared minus a squared equal to 0, a the radius, 0, 0 the center. And if you have a point P, x1, y1 on this circle, then realize that the same thing, you replace in the equation of the tangent, you put g equal to 0, f equal to 0 and c equal to minus a squared and c equal to minus a squared. If you do that, you will get the equation of the tangent to this circle with center 0, 0 and radius a. So the equation of the tangent to this circle will turn out to be x1 plus y1 minus a squared equal to 0 will be the equation of the tangent to this circle. x1 plus y1 minus a squared equal to 0. Got me? Now, yet another terminology, jargon which requires introduction is, I have given you what S is. S is only an expression. Could either be this expression or this expression. In either case, we are talking of a circle, right? Now, the other expression with which you want to breed mental familiarity is the expression just this expression or this expression. So, be it this or this, I call it as T. Just T. Just this expression would be referred to as some T. x1 plus y1 plus g into x plus x1 plus f into y plus y1 plus c is only an expression. Or this T could also be x1 plus y1 minus a squared. And I want you to forcibly write it down. Since you are just starting coordinate geometry, write down. T is only an expression. And if x1 y1 and if x1 y1 be a point on the circle, if x1 y1 be a point on the circle, then t equal to 0. Only then t equal to 0 represents the equation of the tangent at x1 y1. If, write down, if x1 y1 is not a point on the circle S equal to 0, then t equal to 0 would represent some other geometrical entity which we will discuss in a while. So for the time being, just write down. So if x1 y1 be a point on the circle, then t equal to 0 will represent the equation of the tangent at x1 y1. But if x1 y1 be a point outside the circle, then the expression t will still be this. Then what would t equal to 0 represent in that case? That's the question. What would t equal to 0 represent in such a case? Clear? That's what we'll discover in a short while. So if x1 y1, I repeat, is a point on the circle, then t equal to 0 represents the equation of the tangent at x1 y1. But if x1 y1 be a point not on the circle, then what does t equal to 0 represent? What geometrical entity does t equal to 0 represent? Well, one thing, in either case, it will represent a straight line. T equal to 0, whether x1 y1 be a point on the circle or not on the circle, t equal to 0 will always represent a straight line. In one case, that straight line is a tangent. In the other case, what is that straight line? That's what we have to figure out. You know what I'm saying? Okay. Just out of simplicity, let's take the circle, say x plus y squared minus a squared equal to 0. Let's take the circle s equal to 0, x squared plus y squared minus a squared equal to 0. Clear? Imagine a point P, x1, y1 outside the circle. Imagine a point P, x1, y1 outside the circle. Clear? Now, from this point P, how many tangents could be drawn to the circle? 2. Now, it's another story that I have not told you why 2 tangents can be drawn from an external point. It's some joker down way back who told you 2 tangents can be drawn to a circle. But then there is no conclusive evidence that anyone has offered to you why 2 tangents, why not 3 tangents from an external point P. But I'll come to that. And why no tangent can be drawn from points inside the circle. But wait for a little while. Let me be done with it, and then I'll tell you why exactly 2 tangents can be drawn from an external point. Right? Now, there is a point P, x1, y1 outside the circle, right? So, this is the point P, x1, y1 drawn to the circle S, which is x squared plus y squared minus a squared equal to 0. Clear? These are the 2 points of contact, A and B. Do you know the coordinates of A and B? Do you know the coordinates of A and B? No, you don't. Obviously, you don't, right? But then you can pretend that you know, isn't it? You can still pretend that you know. So let's pretend that we know A and B. You know what I'm saying? Let's say A is x prime y prime and B is x double prime y double prime. B is say x double prime y double prime. We are only pretending that we know A and B. Once out of this pretentious assumption, we can use x prime y prime and x double prime y double prime. Once we are done with it, we can dump it, right? So then, now the line joining A and B is a straight line. The line joining A and B is a straight line, and this straight line AB is called the chord of contact. Is called the chord of contact of the circle with respect to the point x1 y1. With respect to the point x1 y1, AB is the chord of contact of the circle with respect to the point x1 y1. If you select some other x1 y1, you'll have some other chord of contact. Different points P will give you different chords of contact. Okay. Now, let's try and find out the equation of the chord of contact. Let's try and find out the equation of the chord of contact. How great it would have been if we actually knew x prime y prime and x double prime y double prime, in which case, given 2 points, you can readily find the equation. Unfortunately, we don't know. So then, what is AP? AP is a tangent at x prime y prime. What is AP? AP is a tangent at x prime y prime, yes or no? Right? AP, tangent at x prime y prime. And like I've already told you, the equation of the tangent at x prime y prime is going to be given by xx prime plus yy prime minus a squared equal to 0 would be the equation of AP, the tangent at x prime y prime, right? BP. That's the tangent at B. That's the tangent at B. Yes or no? Tangent at x double prime, y double prime. And the equation of BP then is going to be x double prime plus y double prime minus a square equal to 0. That's the equation of the tangent at B. Yes or no? All right. Now, AP passes through the point x1, y1, isn't it? This is the equation of AP. That means any point xy on AP will satisfy this equation. London bhai, right now? Any point xy on AP will satisfy this equation, right? So x1, y1 is one of the xy's on AP. So x1, y1 will satisfy this equation, yes or no? x1, y1 will satisfy this equation, clear? So in this, if you replace x by x1 and y by y1, then this equation would be satisfied. How about it? Are you there with me? Right? So x1, y1 satisfies this equation. That means I can replace x and y by x1, y1. Right? So if I did that, lies on AP, which gives me, placing x and y by x1, y1 gives me x prime x1 plus y1 minus a squared equal to 0. Right? Hey, but x1, y1 also lies on BP. Now, this is the equation of BP. All points x comma y on BP will satisfy this equation. So, x1, y1 will also satisfy this equation. I can replace x by x1 and y by y1. Right? So, then x1, y1 also lies on BP. Giving me what? Replace xy by x1, y1. That's like x double prime x1 plus y double prime y1 minus a squared equal to 0. Yes or no? All right. So far so good, right? No issues with it. But let's not lose sight of what we started with. Objective of this entire exercise was to find the equation of AB, the chord of contact with respect to an external point, P, x1, y1. Clear? That was the objective. So then, without attempting to deviate from that objective, these two equations 3 and 4, ogle at them, stare at these two equations with conviction and observe a structural similarity. Observe a structural similarity. Look, both equations 3 and 4, are like this. Something into x double prime, something into x double prime, something into x1 plus something into y1 minus a squared equal to 0. Both are of this format. Both are of the format something into x1 plus something into y1 minus a squared equal to 0. Yes or no? Where equation 3, these blanks have to be filled by x prime y prime, whereas in equation 4 these blanks have to be filled by x double prime y double prime. That's the only difference, right? So structurally, they look similar. They are like this. Equation 3, I repeat, is about filling these blanks with x prime, y prime. Equation 4 is about filling these blanks by x double prime, y double prime. Yes or no? So what we do is to accommodate both x prime, y prime and x double prime, y double prime, we create a representation of the following kind. I think of a x1 and a y1 minus a squared equal to 0. What is equation 3? When this xy is replaced by x prime, y prime. What's equation 4? When this xy is replaced by x double prime, y double prime. Yes or no? You know what I'm saying? Equation 3 is about replacing this xy by x prime, y prime. Equation 4 is about replacing this xy by x double prime, y double prime. Yes or no? Right. Having said this, then first of all, for a split second, forget everything that we've done. If I just give you this and ask you to comment on the nature of the geometry represented by this, what would you say? The straight line? Something into x plus something into y plus something equal to 0 is a straight line. For sure, it's a straight line. This equation 5 is a straight line for sure. It's a straight line for sure. Is it not? It's a straight line for sure, right? Now, my question to you is, does x prime, y prime lie on this straight line? How would you know if x prime, y prime lies on this straight line? If you replace x and y by x prime, y prime, and if this is still 0, then x prime, y prime lies on the straight line. You know what I'm saying? If you replace x and y by x prime, y prime, and if this is still 0, then x prime, y prime lies on the straight line. And therefore, does it lie on the straight line? Yes, sir, it does. Look, if you replace x, y by x prime, y prime, you get this equal to 0. So that expression vanishes when you replace. See, if you replace x by x prime and y by y prime, what would you get? X prime x1 plus y prime y1 minus a squared is what you get. But is this 0? Yes. Refer to 3. It is 0. That means x prime y prime lies on this line. Yes or no? X prime, it's a straight line, and x prime y prime lies on this line. Again, question 2. Does x double prime y double prime lie on the straight line? Yes, it does. Because when you replace x by x double prime, y by y double prime, you get x1 x double prime, y1 y double prime minus a squared, which also is 0. So x double prime y double prime also lies on the straight line. So this is a straight line on which x prime y prime lies, and this is a straight line on which x double prime y double prime also lies. Yes or no? So this is a straight line passing through A and B. This is a straight line passing through A and B. How many straight lines will pass through two given points? 1. So what does this represent? Does it not represent AB? The only straight line that can pass through both A and B is the chord of contact. The only straight line that passes through 2 points A and B is, in this case, the chord of contact. Yes or no? So what does this represent? This therefore is the chord of contact. This is the equation of the chord of contact with respect to an external point, x1, y1. Yes or no? You there with me? Right? So then, what have you learnt about this expression though? Forget the right hand side. X1 minus y plus y1 minus a square is what expression? Is the expression we have referred to as t. T, don't call it tangent, it's t. This expression I have called t. Yes or no? And if x1, y1 is a point outside the circle, then t equal to 0 does not represent the tangent, it represents the chord of contact. It represents the chord of contact. Yes or no? If x1, y1 is a point on the circle, then t equal to 0 represents the equation of the tangent at x1, y1. But if x1, y1 is a point outside the circle, then t equal to 0 will represent the chord of contact with respect to x1, y1. See, the same expression xx1 plus y1 minus a squared, right? If x1, y1 is a point on the circle, it represents the equation of tangent. T equal to 0 will give me the tangent. if x1, y1 is a point outside the circle, then t equal to 0 will represent the chord of contact with respect to x1, y1. Are you fine with this or not? That's what I said. You know, when I made you write that thing earlier, it represents something else geometrically. It represents the chord of contact if x1, y1 is a point outside the circle. Now, doesn't it seem like bizarre coincidence? The same expression t, if x1, y1 is a point on the circle, represents the tangent, and if it's outside the circle, represents the chord of contact. Look, it's no major coincidence. Think of the, I hope you're comfortable with what I've said so far, right? Now I'll try and connect the two things. Right? Think of this as a rigid circular wire, and these two tangents as also rigid wires, Alright? Think of this point P. Take a hammer. Right? Hammer this at P. The two tangents will open up. Yes or no? The two tangents would open up. While you hammer this, x1, y1 changes. It comes closer and closer to the circle. And you get different chords of contact. While x1, y1 changes position, you get different chords of contact. Yes or no? You know what I'm saying? And eventually, in a limiting case, when this guy comes and sits neatly on the circle while you are hammering it all the way, the two tangents would open up completely like this and will become one single tangent. And the point P, therefore the chord of contact has now become a tangent. Do you realize that when you keep hammering, the chord of contact comes closer and will become a tangent? You know what I'm saying? So there is a connectivity. It's not out of no reason that the same expression eventually, based on where x1, y1 was lying, gave me two different things, which actually was not two different things. Turned out to be two similar things, not completely different things, right? These two tangents will become a single tangent if x1, y1 eventually was lying here, and therefore this becomes the new chord of contact. So the chord of contact, or rather the tangent, is only a special case of the chord of contact. If x1, y1 was lying on the circle, the tangent, the chord of contact became a tangent. Right? Are you comfortable with this? You understand everything that I've said? Right? And again, like I said, whether it's this circle x squared plus y squared minus a squared equal to 0, or the general circle x squared plus y squared plus 2gx, etc., g equal to 0, based on whether x1, y1 is lying on the circle or outside the circle, will either represent a tangent at that point or will represent the chord of contact with respect to that. No issues with this, clear? Let's say this is a circle S, which is x squared plus y squared minus a squared equal to 0. This is the center, which is 0, 0 for this circle. Center, which is 0, 0 for the circle. Clear? Now, say x1, y1 is a point inside the circle. Say x1, y1 is a point inside the circle. So the point x1, y1 is inside the circle. With every point P inside the circle, I repeat, with every point P inside the circle, A chord of the circle could be drawn whose midpoint is that point. One chord of the circle could be drawn whose midpoint is that point. If you take any point inside the circle, take any point inside the circle, right? And this is the center of the circle. This is the center of the circle. You can always draw a chord. You can always draw a chord whose midpoint is P. Whose midpoint is P. For every point P inside the circle, a chord could be drawn whose midpoint is P. And exactly one chord could be drawn whose midpoint. Exactly one chord could be drawn whose midpoint is a given point P inside the circle. Okay, so now there is just any other point inside the circle, and we end up drawing a chord AB whose midpoint is P. Whose midpoint is P. Midpoint of AB. Midpoint of AB. P is midpoint of AB. For every P, there is a unique AB whose midpoint is P. Now, if I want to find the equation of the chord whose midpoint is P, so my next objective is to find the equation of the chord whose midpoint is a point x1, y1. Find the equation of a chord whose midpoint is the point x1, y1. Chord whose so now if you join the center to the midpoint, then it's going to be perpendicular to the chord, right? If you join the center to the midpoint of a chord, it's going to be CP will be perpendicular to the chord, right? What's the slope of CP? Y1 minus 0 divided by x1 minus 0. The slope of CP is y1 minus 0 by x1 minus 0. That's the slope of CP. So then, what's the slope of AB? Minus x1 by y1, because these two are perpendicular lines. So no, now I know the slope of AB, I know a point on AB, right? The equation of AB chord AB is y minus y1 by x minus x1 equal to the slope, right? Y1 minus x1 by y1. Clear? Yes or no? This I can write as xx1 plus yy1 equals x1 squared plus y1 squared. Cross multiplying and collecting terms. Subtracting a squared from both sides. What is this expression referred to as? T. What is this expression referred to as? S1. S1. This is S1. If this was S, then replacing x and y by x1, y1 is S1. So this is S1 and this is T. So in which case, T equal to S1 will represent what? Equation of the chord in terms of its midpoint x1, y1. Equation of the chord in terms of its midpoint x1, y1. How about it? Do you understand this? Right? T equal to S1 is the equation of a chord in terms of its midpoint x1, y1. So if the midpoint is known x1, y1, then you simply write t equal to s1. You'll get the equation of the chord in terms of its midpoint, be it for this circle or the general circle, right? And realize, I'll tell you whatever I'm telling you right now, the equation of the chord of contact if x1, y1 is a point outside, that is t equal to 0, or equation of the chord in terms of its midpoint represented as t equal to s1. All of this will get inherited by parabola and then ellipse and then by hyperbola. It's just going to be replication. So it's learning coordinate geometry is only a one-time effort. Get your circles right, the parabolas, the ellipses and the hyperbolas will fall at your feet, right? But then this is just single unit of effort which you will have to plunge. Okay, so t equal to s1 will represent the equation of the chord of contact, the chord in terms of its midpoint x1, y1, right? Now, say this is a circle, say S, which is x squared plus y squared minus a squared equal to 0. Center C of the circle 0, 0. Now, this is a straight line. Say y equal to mx plus c. This is a straight line, y equal to mx plus. In general, a straight line would intersect the circle at 2 points. Those 2 points could be real and distinct like this, or could be real and coincident. When these 2 points come closer and closer, the 2 points become real and coincident, or the straight line could intersect the circle at 2 imaginary points. Does not intersect the circle in common parlance, right? 2 distinct and real points, 2 coincident real points, 2 imaginary points, right? That means does not intersect. These are the various orientations of a line with respect to a circle, right? Now, the line is like mx minus y plus c equal to 0 is the line, right? The distance of the center from the line, the distance of a point from a line, you recall the perpendicular distance of a point from a line is magnitude of, from 0, 0, replace x by 0, y by 0, mod c, divide by m square plus 1 square, right? Coefficient of x squared and coefficient of y squared. That's a perpendicular distance of 0, 0 from this line, perpendicular distance of a point from a line, right? Now, if this d is less than the radius, then this case emerges. If this d is equal to the radius, in this case d is equal to the radius a, then this case emerges. If the perpendicular distance d is greater than the radius a, then this case emerges, right? So d less than the radius will give me 2 distinct real points. D equal to the radius, 1 point or 2 coincident points. D greater than the radius will give me 2 imaginary points, or the line does not intersect the circle at all, right? So, very clearly, for this case, D must be equal to the radius for this case, right? That means mod C must be a root 1 plus m squared. D equal to a will give me mod C equal to a root 1 plus m squared, or I get C equal to plus minus a root 1 plus m squared. If I remove the modulus, then a plus and a minus sign would emerge, right? Which means the equation of a circle equation of a circle x squared plus y squared minus a squared, the equation of, this is the case of a tangent. This is the case of a tangent. That means y equal to mx plus c will become a tangent to the circle, if c is plus minus a root 1 plus m squared, if c is plus minus a root 1 plus m squared. So y equal to mx plus minus a root 1 plus m squared will represent what? A tangent to the circle. Now, m is the slope of the tangent. As you can see, m is the slope of the tangent. If you select different m's, you get different tangents to the circle. If you select different m's, you get tangents at different points. That means different tangents to the circle. Yes or no? So then, if m is looked upon as a parameter, this will represent family of tangents to the circle. Yes or no? The entire bunch of tangents to the circle can be obtained by simply plugging in different values of m. So in general, and I could just use plus sign, one of the signs could be used. So in general, I can say, let's say y equal to mx plus a root 1 plus m squared for different values of m will represent family of tangents to the circle, Different tangents will subscribe to different values of m. Right? So if m is a parameter, this would be looked upon as a family of tangents to the circle. Now, look, so this was the circle S, which is x squared plus y squared minus a squared equal to 0 was the circle. Clear? This was a certain tangent. That means this tangent must be for some m, mx plus a root 1 plus m squared must be the equation of this tangent. This tangent must be y equal to mx plus a root 1 plus m squared for some m. Yes or no? Now say this tangent at P passes through a point Q, which is say x1 y1, passes through P, which is Q, which is x1 y1. That means x1 y1 lies on the tangent. That means x1 y1 lies on the tangent. That's you. So y1 is mx1 plus a root 1 plus m squared. x1 y1 satisfies this equation because it lies on the tangent, right? Or where m is what? M is the slope of the tangent from x1 y1 to the circle. Yes or no? M is the slope of the tangent drawn from x1 y1 to the circle. Can I say this or not? Right? I can then say, so if I solve for m, what would I get? If I solve this equation for m, I'll get the slope of the tangent from x1 y1 to the circle. Clear? So y1 minus mx1 whole squared is a squared into 1 plus m squared. When I square, then this is what happens. y1 minus mx1 whole square is a square into 1 plus m squared. Right? Look, are you fine with this? So which means now x1 squared minus a squared into m squared minus x1 y1 into m plus y1 squared minus a squared equal to 0. Putting all in one place, right? Putting all in one place, see m squared, x1 squared minus a squared, then the middle term 2 x1 y1 m, and then y1 squared minus a squared. which is what? A quadratic in M. It's a quadratic in M. Which is a quadratic in M. And when you solve for M, by the way, what would you get? You get the slope of the tangent from x1, y1 to the circle. Right? When you solve for M, you'll get the slope of the tangent from x1, y1 to the circle. Clear? You know what I'm saying? Hey, but two values of M will emerge. That means in general, two tangents can be drawn. In general, two tangents could be drawn from a point x1, y1 to the circle. It's another story. These two tangents could be real and distinct. They could be coincident or they could be imaginary. So let me see, when would these tangents from x1, y1 turn out to be real and distinct? They would be real and distinct if the two values of M obtained are real and distinct. When would the roots of a quadratic be real and distinct? When the discriminant is greater than 0, right? So this is a quadratic having roots M1 and M2. In general, therefore, from Q, two tangents could be drawn, one with slope M1, the other one with slope M2, one with slope M1, other one with slope M2, where M1 and M2 are the roots of this quadratic, right? For the two tangents as shown in the figure to be real and distinct, so M1 and M2 have to be real and distinct for the two tangents to be real and distinct. We have discriminant of the quadratic greater than 0. Discriminant of the quadratic greater than 0. Right? What's the discriminant of the quadratic? 4 2x1 y1 whole square minus 4 times x1 squared minus a squared into y1 squared minus a squared greater than 0. This would cause the tangents to be real and distinct, right? No issues with this. Now realize, when I multiply this out, 4x1 y1 squared would get cancelled with 4x1 y1 squared. What we are then left with is a squared x1 squared plus a squared y1 squared greater than a to the power 4 is what we get. Yes or no? Or which would mean x1 squared plus y1 squared greater than a squared, right? Which in turn would mean x1 squared plus y1 squared minus a squared greater than 0. S1 greater than 0. That means x1, y1 must be a point outside the circle. That means x1, y1 must be a point outside the circle. S1, this is S1 greater than 0, implying that Q must be outside the circle. And that's why from points outside the circle you have two real and distinct tangents, right? And if you took discriminant less than 0, then you will have imaginary tangents and you will get x1 squared plus y1 squared minus a squared less than 0. That means x1, y1 must be a point inside the circle. And therefore, from points inside the circle, you don't have real tangents, right? And if the discriminant is equal to 0, the two tangents would become coincident. And then you will get x1 squared plus y1 squared minus a squared equal to 0. That means point on the circle. So you realize why from an external point two tangents can be drawn? From a point on the circle, just one tangent. From points inside the circle, no tangent, there is no real tangent. Two imaginary tangents, all right. But you can continue to imagine that, right? पानी चाहिए तेरे को कुछ और चाहिए हाँ बोल दे, जुगाड़ कर देंगे। मैंने इस फ्रूटी चाहिए हो सकता है, कोल्ड ड्रिंक चाहिए हो सकता है, तुमको और क्या क्या चाहिए बताओ। नहीं नहीं, पब्लिकली बताओ, सभी अपने ही हैं, बता दो तुम्हारे लिए क्या व्यवस्था करें। कुछ ओएज ग्रुप का चाहिए। सही बोला। मतलब कम से कम ये गड़बड़ सोचता है, वो तो है। ऑलराइट, सो फार सो गुड, नो इश्यूज विद दिस, राइट? नाउ if this is a circle, any center, there could be points P, there could be points P such that from these points, if you draw tangents to the circle, from points outside the circle, like we've already demonstrated, there would be a pair of real and distinct tangents. A pair of real and distinct tangents could be drawn from every point P outside the circle, right? From every point P outside the circle, a pair of real and distinct tangents could be constructed to the circle. All right. Now, there is a bunch of points P such that from these points, if you draw tangents, then these tangents would be perpendicular. There exists a set of points P. There exists a set of points P such that from these points, if you draw pairs of tangents, then these tangents would be mutually perpendicular or orthogonal. The locus of such points P is called the director circle. The locus of such points P, locus of P from which perpendicular tangents could be drawn, is called the director circle of the given circle. Right? See, there are very many points P such that from those points, if you draw tangents, that the tangents would be orthogonal perpendicular, right? And if you collect all those points, then they constitute a locus which is called the director circle, right? Now, very easy to see if the two tangents are perpendicular. Let's say this is one of the tangents, this is one of the tangents, the other tangent is, let's say, PB. Then the line joining the center to P will bisect this angle. So if this entire thing is 90 degrees, this is going to be 45 degrees. Do you realize that? Half the angle is going to be 45 degrees. Now, if A is the radius of the circle, if A is the radius of the circle, then do you realize that this is going to be A root 2? This is going to be A root 2. A by sine 45 degrees, this will be A by sine 45 degrees. Which means what? Distance of P from the center C will be root 2 times the radius of the mother circle. This is the mother circle. And if the point such that the tangents from this point are perpendicular to each other, then this point must be root 2 times the radius of the mother circle. Must be at a distance equal to root 2 times the radius of the mother circle. That means if you, the point P must be at a fixed distance A root 2 from C. The point P must be at a fixed distance A root 2 from C, which means what? If this is the mother circle whose center is C, then the point P could lie anywhere on this circle whose radius is A root 2. The point P could lie anywhere on the circle whose radius is A root 2, yes or no? All points on the circle whose center is C and whose radius is A root 2, all points on the circle whose center is C and is A root 2 would produce tangents to the mother circle that are perpendicular or orthogonal, yes or no? Shall I explain again? No? Huh? You fine with this? So this circle must be the director circle. Why? Because from any point on this circle, if you draw tangents, they would be perpendicular. Tangents to the mother circle. This is the mother. Do you realize that this outer circle and the mother circle are concentric? They have the same center, and the radius of the director circle is root 2 times the radius of the mother circle, right? So that's the important thing. That's the important thing. The director circle is concentric with the mother circle. The director circle is concentric with the mother circle and has a radius which is root 2 times the radius of the mother circle. So in a general sense, if this center is 0, 0, then the radius of this is a root 2. Then any point xy on the director circle, any point xy on the director circle would be what? Distance of P from 0, 0, that is x square plus y squared, must be a root 2 whole square. That means x squared plus y squared must be 2a squared. That must be the director circle. Given the mother circle to be, say, x squared plus y squared equal to a squared, the director circle is x squared plus y squared equal to 2a squared. The director circle has the same center as the mother circle, but its radius is root 2 times the radius of the mother circle. And what's the property of any point on the director circle? If you draw tangents to the mother circle from any point on the director circle, they would be perpendicular to each other. That's it. Clear? So we understand this idea of a director circle. We understand a little bit of tangents, right? Is there any confusion on anything that I have taught so far on circles? Any confusion, anything that still bothers you? You understand that the chord of contact is t equal to 0 if x1, y1 is a point outside the circle. If it's a point on the circle, t equal to 0 represents the equation of the tangent to the circle. And if x1, y1 be a point inside the circle, then t equal to s1 represents what? The equation of the chord whose midpoint is x1, y1. Do you understand all of this? Relative orientation of a point with respect to a circle, inside, on or outside, based on s1 less than 0, equal to 0 or greater than 0. All of that is fine, perfectly fine with you, right? Okay. Now, say this is a circle x square plus y square minus a square equal to 0. Center 0, 0. And let's say there is a point P outside the circle. Let's say there is a point P outside the circle. Say its coordinates are alpha comma beta. Say its coordinates are alpha comma beta. From P, I draw a tangent PA and another tangent PB. P, I draw a tangent PA and another tangent PB. First of all, how many points will uniquely determine a circle? I assume that you know that. How many points do you need to determine a circle? Okay, how many points do you need to determine a straight line? How many points do you need to determine a circle? 3 non-collinear points. 3 non-collinear points will uniquely determine a circle, right? So, given a point P, there would be 2 other points of tangency A and B. So how many circles will pass through P, A and B? 1. Given 3 points P, given a point P, A and B would be unique. So P, A and B are 3 fixed points. So a unique circle will pass through these 3 fixed points. Now my contention is, what's the equation of the circle passing through P, A and B? What's the equation of a circle P, A and B? Equation of a circle passing through P, A and B. Join A to C. Going to be perpendicular, radius perpendicular to the tangent. Join C to B. That's also going to be perpendicular to PB. Right? Join C and P. So PACB is a quadrilateral, yes or no? And the nature of this quadrilateral? Yes, cyclic. Why? This plus this, 180 degrees. It's a cyclic quadrilateral, yes or no? A pair of opposite angles supplementary will cause it to become a cyclic quadrilateral, right? So PACB is not just a quadrilateral but is a cyclic quadrilateral. Cyclic quadrilateral. Bolo. Okay. Which means what? P, A, C and B lie on the same circle. What it means? When I say it's a cyclic quadrilateral, that means these are points lying on the same circle. P, A, C and B. There could be a circle constructed to pass through P, A, C and B. That's what is meant by cyclic quadrilateral. All those 4 points must lie on the same circle, right? So there exists a circle that passes through P, A, C and B. Do you realize what I'm saying? There is a circle that passes through P, A, C and B. Which means the circle that I'm looking at, the one that passes through P, A and B must also pass through C. That's what it means. The circle that passes through P, A and B must also pass through C, right? This is what I'm seeking, the circle passing through P, A and B. But the same circle must also pass through C because P, A, C, B are concyclic points. They lie on the same cyclic quadrilateral. Are you confused? No? Alright. So then, the problem says this, and you can say, alright, I'm looking at a circle passing through not only P and B but also passing through C. Very simple. Do you realize that this is 90 degrees and this is the circle that I'm seeking? And if this is 90 degrees, this must be angle in a semicircle. That means PC must be the diameter of the required circle. That means PC must be the diameter of the required circle, yes or no? PC must be the diameter of the required circle, right? Got me? Abnava, right? Right. Now if PC is the diameter, I know the endpoints of the diameter, x1, y1, x2, y2. Given the endpoints of the diameter of a circle, I can find the equation of the circle, x minus x1 into x minus x2 plus y minus y1 into y minus y2 equal to 0. Is the equation of the circle in terms of the endpoints of the diameter of the circle. Clear? Right? So, PC is the diameter of the required circle. So, equation of the circle will be what? X minus 0 into x minus alpha plus y minus 0 into y minus beta equal to 0 would be the required circle, which is like x squared plus y squared minus alpha x minus beta y equal to 0 is the required circle. Make sense? Hmm? Now, say I give you two circles. Say I give you two circles. I still have my commitment not failing. S, which is x square plus y square plus 2gx plus 2fy plus c equal to 0 is one circle, right? And say another circle is S prime, which is x square plus y square plus 2g prime x plus 2f prime y plus c prime equal to 0 is another circle. Hmm? The center of the circle is minus g minus f. The radius of the circle is root g square plus f square minus c. The center of the circle is minus g prime f prime. Root g prime f prime, root g prime squared plus f prime squared minus c prime is the radius of this circle, right? And let's say these circles intersect at real points, not necessarily distinct. Let's say they intersect at real points. Now, obviously, you know the condition for them to intersect at real points. The distance between their centers, must be less than the sum of the radii, greater than the difference of the two. Let's say intersect at two distinct real points. May or may not be distinct, but at least 2 points, 2 real points. This is S equal to 0 and this is S prime equal to 0. Let's say these circles intersect. That's all that they intersect. The two real points or two coincident points will not matter. So in general, A is one of the points of intersection, B is the other point of intersection. A is one of the points of intersection, it lies on both the circles. B is another point of intersection, this also lies on. Given 2 points, how many circles will pass through 2 points? Infinite, isn't it? If I just give you 2 points, A and B, right? And my question is, how many circles will pass through these points? What you can do is construct the perpendicular bisector of AB and look at any point C on the perpendicular bisector with C as the center and CA or CB as the radius. One circle could be drawn for any C on this perpendicular bisector. For different C's, you will have different circles passing through A and B. So, given two fixed points A and B, infinity of circles could be drawn. A family of circles could be drawn through two fixed real points. Yes or no? Given two fixed real points, infinity of circles could be drawn through those two fixed points. Whereas these two are two fixed circles. S and S prime are two fixed circles passing through A and B. These are just two amongst the very many. These are just two amongst the very many circles that pass through A and B, right? These are two fixed circles. But there are many more circles passing through A and B. There are many more circles passing through two fixed points A and B. Say, for example, this could be one circle, and so on and so forth, right? Many more circles could pass through A and B, the intersection of two fixed circles, S and S prime. Okay, now answer the following. First of all, if I write S plus lambda S prime equal to 0, S plus lambda S prime equal to 0, which is referred to as a linear combination of S and S prime, like I did in straight lines. L plus lambda L prime equal to 0 was a linear combination of L and L prime. This is a linear combination of S and S prime. This is a linear combination of S and S prime. Let's first try and understand what this represents. Try and understand what S plus lambda S prime would eventually represent. What geometric entity would S and S prime represent? Well, you write S as x square plus y square plus 2gx plus 2fy plus c plus lambda x square plus square plus 2g prime x plus 2f prime y c prime equal to 0. That's s plus lambda s prime equal to 0, a linear combination of two circles, right? Which I could also write as 1 plus lambda into x squared plus 1 plus lambda into y squared plus 2x into g plus g prime lambda plus 2y into f plus f prime lambda plus c prime lambda equal to 0, yes or no? I will assume that lambda is not minus 1. I will assume that lambda is not minus 1. Lambda can take other values except minus 1, let's say in this case, the case that I am considering right now, right? Now, I divide by 1 plus lambda both sides. I divide by 1 plus lambda both sides. I get x square plus y square plus 2g plus g prime lambda by 1 plus lambda into x to f plus f prime lambda by 1 plus lambda to y c plus c prime lambda by 1 plus lambda equal to 0. This is what I get as the equation. Hey, but what is this? It's a circle. Realize that x square plus y square plus something into x plus something into y plus something equal to 0 is the form of the equation of a circle, right? So then conclusion number 1. If s equal to 0 is a fixed circle and s prime equal to 0 is another circle, then a linear combination of two circles would still be a circle, So s plus lambda s prime equal to 0 always represents a circle, will always represent a circle. Clear? That's conclusion number 1. Easy to see. And even easier to see, if you vary lambda, as long as lambda is not minus 1, because lambda equal to minus 1 will cause this to be undefined, right? So as long as lambda is not minus 1 and you vary lambda, you will still get a circle, but you will get different circles for different values of lambda. Yes or no? Are you there with me? S plus lambda s prime equal to 0 represents a circle. If s equal to 0 is a fixed circle, s prime equal to 0 is a fixed circle, then s plus lambda s prime equal to 0 will represent a circle. For different lambdas, you get different circles out of it, right? So s plus lambda s prime equal to 0 represents for sure a bunch of circles. I do not know whether it's a family or not, because with a family I must identify a common trait. Right now all that I can say is that s plus lambda s prime equal to 0 is a bunch of circles. For different values of lambda I get different circles out of it, given two fixed circles s equal to 0 and s prime. So far so good or not, right? Now the important thing, there is no confusion in whatever I have communicated so far, right? Now the closing remark here is, which is very easy to see. Bunch of circles. So far a bunch. So far just a bunch. Different lambdas will give me different circles out of this linear combination of s and s prime, right? Now, point A, does it lie on s equal to 0? Does it lie on s prime equal to 0? That means coordinates of A when plugged into S will cause S to become 0. The coordinates of A when plugged into S prime will cause S prime to become 0. What I want to check is if A lies on this circle or not. I want to check if A lies on this bunch of circles or not. A is a fixed point. These are two fixed circles, A and B are two fixed points. I want to see if A lies on this circle or not for any lambda, right? The coordinates of A will cause S to be 0. The coordinates of A will cause S prime to be 0. So, coordinates of A will cause S plus lambda S prime to become 0. Yes or no? That means the point A lies on this circle. The point A lies on this circle, right? Similarly, for B, If A lies on this circle, similarly, B also lies on this circle, right? So this represents if S equal to 0 is a fixed circle and if S prime equal to 0 is another fixed circle, having two fixed points of intersection. Two fixed circles will have, in general, two fixed points of intersection, A and B. Then S plus lambda S prime equal to 0, write down. A linear combination of two circles for lambda not equal to -1. A linear combination of two circles for lambda not equal to -1. Two fixed circles. Two fixed circles. Will give me a family of circles. Now it's not anymore a bunch, it's a family, because all members of the family will pass through A and B. So for lambda not equal to -1 will give me a family of circles passing through the intersection A and B, passing through the intersection A and B of the two fixed circles, Which means, you know what? You didn't even have to know what exactly are the coordinates of A and B. And you can always close your eyes and say, well, any other circle that passes through A and B will still be of the form S plus lambda S prime equal to 0. You can choose to plug in different values of lambda. You can choose to plug in different values of lambda, and you will still get a circle passing through A and B. Different lambdas will produce different circles, but all these circles will necessarily pass through A and B, the two fixed points of intersection of the two fixed circles S equal to 0 and S prime equal to 0. This is a very important thing to understand. Extremely important thing to understand, right? No confusion, right? No confusion. Now, you have to leave? You'll attend? Okay. Now, I've ignored the prospect of lambda being equal to -1 so far, because lambda equal to -1 would have caused all of this to be undefined, right? Could no longer have been a circle. Say if lambda were to be equal to -1. Now this case, when lambda was -1, if lambda was -1, then what am I going to get? S minus S prime equal to 0. Now, one thing, whatever S minus S prime is, it's some curve, let's say. S minus S prime equal to 0 is some curve. And I want to see if A lies on this. Yes, A will lie on this. Why? Because if you plug in the coordinates of A in S, S will be 0. If you plug in the coordinates of A in S prime will be 0. So if you plug in the coordinates of A in S minus S prime, so that's going to be 0. So A will lie on this geometric entity. Similarly, B will also lie on this geometric entity. So whether lambda is -1 or lambda is not -1, S minus S plus lambda S prime equal to 0 will always pass through A and B, In the earlier case, when lambda was not -1, it was a circle passing through A and B. But when lambda is -1, it will still pass through the points A and B. Are you lost or are you there with me? Huh? Fine. So when lambda is -1, then S minus S prime, realize, is like 2 into G minus G prime into X plus 2 into F minus F prime into Y plus C minus C prime equal to 0. Which is what? A straight line. It's a straight line passing through A and B. And what are A and B? A and B are the intersection points of two fixed circles, S and S prime. So what does this represent? It represents a straight line passing through A and B. S minus S prime equal to 0 represents a straight line passing through A and B. And a straight line passing through A and B is what? A common chord. So S minus S prime equal to 0 will represent the common chord of the two circles minus S prime equal to 0 will represent the common chord of the two circles, fixed circles S equal to 0 and so on. So if S equal to 0 is a fixed circle, S prime equal to 0 is another fixed circle, then S plus lambda S prime equal to 0 for lambda not equal to minus 1 will represent family of circles passing through the intersection of the two fixed circles. When lambda is minus 1, that is S minus S prime equal to 0, it's going to represent the equation of the common, right? And in fact, if the two circles touch each other like this, then the common chord becomes the common tangent. If the two circles touch each other like this, then the common chord becomes the common tangent. So if S equal to 0 is a fixed circle, S prime equal to 0 is another fixed circle, then S minus S prime equal to 0 for two fixed circles touching each other will represent the common tangent, because now the common tangent is synonymous with the common chord. Synonymous with the common chord. Are you all right? Clear? Say if there is a fixed circle S, which is x square plus y square plus 2gx plus 2fy plus c equal to 0 is a fixed circle. Is a fixed circle, right? And L, which is let's say Lx plus my plus n equal to 0 is a fixed straight line. S equal to 0 is a fixed circle. L equal to 0 is a fixed straight line. Is a fixed straight line. Now, let me look at a linear combination of S and L. Let me look at a linear combination of S and L. S plus lambda L equal to 0. Let's see what this is going to represent. S plus lambda L equal to 0. Let's see what this is going to represent. What is S? S is x square plus y square plus 2gx plus 2fy plus c plus lambda Lx plus my plus n equal to 0. This is S plus lambda L equal to 0. This is S plus lambda L equal to 0. A linear combination of a fixed circle S and a fixed line L. Clear? This I can write as 2g plus lambda L into x, 2f plus lambda m into y plus c plus lambda n equal to 0. What is this? A circle? For sure. If S equal to 0 is a fixed circle, L equal to 0 is a fixed straight line, then S plus lambda L equal to 0 is a circle. Is a circle for sure. For any value of lambda, it's a circle. And for different lambdas, you will get different circles out of it. Yes or no? So bunch of circles to begin with, it's a bunch of circles. So S plus lambda L equal to 0 represents a bunch of circles. For different lambdas, you will get different circles out of it. For different lambdas, you will get different circles out of it. You are assimilating everything, right? Now, In general, a fixed circle will intersect a fixed straight line at two fixed points A and B. Right? A lies on S equal to 0. So the coordinates of A will satisfy this equation. Coordinates of A will cause the expression S to become 0. Yes or no? A lies on this fixed straight line. So if you plug in the coordinates of A in the expression L, then L will become 0. Coordinates of A will cause L to become 0. Right? So now this curve, this circle, S plus lambda L equal to 0 is a circle. I want to see if A lies on this circle. If A lies on this circle for different lambdas. Well, if I plug in the coordinates of A in this, then S will become 0, L will become 0, and therefore this will become 0. Right? That means A lies on this circle, A lies on this circle. For any lambda, A will lie on this circle. Similarly, B will also lie on this circle. Right? So then, S plus lambda L equal to 0 represents now no longer a bunch, it's a family. It represents a family of circles passing through the intersection points A and B of two entities, a fixed circle and a fixed straight line L equal to 0. Write down. If S equal to 0 is a fixed circle, L equal to 0 is a fixed straight line, then S plus lambda L equal to 0, then S plus lambda L equal to 0 represents a family of circles, passing through the intersection A and B, of the fixed circle with the fixed straight line, Right? Of the fixed straight line, fixed circle with the fixed straight line. For different lambdas, surely this will produce different circles. But then all those circles that you can generate out of different lambdas will necessarily pass through these two fixed points, the intersection of this fixed circle with this fixed straight line. You got me this? Day 1 on circles. This should suffice. I assume and I hope you've understood everything that I've said, right? This was important. I've set the foundation for circles, but we still have the journey to cover even as far as the concepts are concerned. But then, with this as the foundation, the journey would get smoother, right? So on Monday, when we continue with more of circles, we'll start from where we've left